Good morning, afternoon, or evening. How y'all doing today? Welcome back to Mr. Morrow's Honors Geometry class. Today we're going to really make things a lot easier for you guys, okay, when it comes to perpendicular bisectors. And we're going to learn about the equidistant theorems. There's two theorems, equidistant theorems. Let's first talk about what distance is, okay? When we're talking about distance, the distance between 2 points or objects is the length of the shortest path joining them. Now, think about that. If I have a point here and I have a point here, the length would not be by coming up here and then going around there, or by going backwards and then going up and then coming down and then around and then going there. That's ridiculous. Okay, that's not going to be the distance. The distance will be the shortest path to the other point. And the shortest distance between 2 points is indeed a straight line. Always. If you have 2 points, the shortest distance between those 2 points is a straight line. So when we look here at segment AB here, the distance between AB is whatever length AB is. That is the distance. That is the shortest path between 2 points, is a straight line, or in this case, a straight segment. Okay, so that is what distance is. When we're talking about distance, we're talking about I have 1 point, I have another point, and the quickest or easiest way to get there, the shortest distance, is by connecting those 2 points with a straight line. Now, if 2 points are the same distance from a third point, then they are what's called equidistant. Equidistant, think about the roots here. Equi comes from equality, equal. When they're equal distances, they're called equidistant. So in this particular case here, I have J, I have F, and I have K. And as you can clearly see, I have labeled with tick marks that JF is congruent to JK. So that means that J is the same distance from F as it is from K. So that means J is equidistant to F and K. Since F and K are the same distance from J, okay, J is that third point, J is equidistant, from both F and K. Yes, sir? No. F and K are not equidistant are not the same distance as F is to J and K is to J. No, that does not mean that. Good question, son. All it means is since J, F is congruent to FK, J is equidistant to both F and K. Yes, sir? They will tell you, they will give you the tick marks, or they will say J is equidistant from F and K. If they tell you J is equidistant from F and K, you know that JF is congruent to JK because J is the same distance to both F and K. As far as proof or geometry goes, we would look at it like this. Since KJ is congruent to FJ, J is then equidistant from F and K. Okay? So that's very important to understand. You gotta really understand the meaning of equidistant. It's extremely important. All right? Now, this is going to help alleviate a lot of heartache when it comes to perpendicular bisectors. It's going to make life a lot easier. Yes, sir? Yes, that's what we just finished saying. That in a proof, they would either have the tick marks there, showing that Fj is congruent to Jk, or they would say Fj is congruent to Jk, or they would say that point J is equidistant to both F and K. Thank you. Great question. All right, now, definition of perpendicular bisector. We kind of defined it yesterday, but now we're going to clarify it, we're going to solidify it, and make it really all come together. Perpendicular bisector, gentlemen, is a combination of both a median and an altitude. That's what it is. Therefore, no. Therefore, a perpendicular bisector is a segment or line that bisects and is perpendicular to another segment. That's what a perpendicular bisector is. Okay? How would we visualize this? Well, right here is a perpendicular bisector. AC here both bisects segment BD and is perpendicular to segment BD. It's a median because a median generates from a vertex, just like AC does, and bisects the opposite segments, okay, from the vertex. That sounded weird. A median bisects the side that is opposite the vertex it is generated from. Sorry. And also it is an altitude because AC forms 90-degree angles. It's perpendicular. So that's what a perpendicular bisector is. It's a combination of both a median and an altitude at the same exact time. All right? Now, if we look at a perpendicular bisector, hopefully this will make the equidistant theorem a lot easier for you to understand. Let's look at just a verbal proof here really quickly. Since we know that BC is congruent to CD, all right, we know that angle ACB and angle ACD are right angles. That means that angle ACB and angle ACD are congruent because of the right angle congruency theorem, right? We know that AC is congruent to itself because reflexive, correct? So don't we automatically now know that triangle ACB is congruent to triangle ACD because of side angle side? And then from there, wouldn't we easily be able to determine that AB is congruent to AD? Do you see that? Okay, yes, sir. Yes, sir, go ahead. Yes, the right angle congruency theorem states that right angles are congruent. The right angle theorem states that if two angles are congruent and supplementary, then they are right angles. Thank you so much. Yes, sir. No, that's why we have the equidistant theorem. Well, the equidistant theorem, what it's going to do is it's going to say, okay, when this theorem occurs, and you'll see in a second what happens, then you have a perpendicular bisector. And then we have the converse of it, okay? But let's first focus on what I was trying to show you guys. Since AB is congruent to AD because of CPCTC, look at what's happening here, guys. I want you to really pay attention and honestly ask questions. That's what I'm here for, I swear. You know that. As much as we play around, you know that I do. Okay. Notice that A, check it out, is equidistant to B and to D, right? And do you also see here, gentlemen, that C is equidistant to B and to D? That's the equidistant theorem. When you have 2 points that are equidistant from the endpoints of the same segment, you're going to form a perpendicular bisector. Now let's clear that up. But I wanted to visually show you the proof behind it because it makes life a lot easier. A lot of people have problems with this because I don't think that they take the time to show you why it occurs. So the equidistant theorem states the following. If 2 points, in this particular case, we're talking about point A and C, are equidistant from the endpoints of a segment, really to be more clear, of the same segment. That would make things a little bit clearer, I believe. So if 2 points, in this case A and C, are equidistant from the endpoints of the same segment, in this case that same segment is BD, then the 2 points determine the perpendicular bisector of that segment. So since A is equidistant to segment to B and D, and C is also equidistant to B and D, and B and D lie on the same segment because they are the same segment, then we know that AC will be the perpendicular bisector of BD. So again, if A and C are equidistant to both B and D, 2 points are equidistant to the endpoints of the same segment, then AC is the perpendicular bisector of BD. Yes, sir.
We already know that it was a perpendicular bisector before.
No, we didn't. We did not know that. All we knew here from the beginning here was that AD and AB are congruent. CB and CD are congruent. That's all we know. Now we can prove now, because if we say AC is congruent to itself, then triangle ACD is congruent to triangle ACB. Then we can say that angle ACB is congruent to angle ACD because of CBCTC. If 2 angles are congruent and supplementary, then we know they're right angles, then boom, that is a perpendicular bisector. We're circumventing all of that now. Now what we're saying is, since A and C are both equidistant to the endpoints of the same segment, in this case BD, now we know that AC is a perpendicular bisector of BD. Yes, sir?
So we're just making it a quicker way.
We're making it a much quicker way. We don't have to go through whole proving that the triangles are congruent, proving that it's CPCTC, proving the right angle theorem. We go right to the point of it. Yes, sir. You could abbreviate equidistance as equi. Yes. If it's so difficult to put equidistance, I guess that would be acceptable. Okay. Now, does that make sense, guys? Yes, sir.
So if we were trying to perpendicular bisector, for the reason, we would say like, oh, point such and such is a perpendicular bisector because of the equidistance theorem.
Correct. You would use the equidistance theorem to prove that a segment is perpendicular bisector to another segment. Absolutely. Yes, sir. Are you sure? Okay, thank you, sir. Now, let's look at the converse of that. Okay? The converse of the equidistant theorem. If a point is on the perpendicular bisector of a segment, then it is equidistant from the endpoints of that segment. What am I saying? Okay. I tell you right from the beginning, AC is the perpendicular bisector of BD. If that's the case, guys, for sure, 100%, you don't have to prove triangles congruent anymore. You don't have to use CPCTC. You don't have to use the right angle theorem. If I tell you right from the bat, from the get-go, that AC is perpendicular bisector of BD, boom, then you know that AB is congruent to AD and BC is congruent to CD. Done. Bingo, bango, bongo. Done. Sir, my brother. Remember what converse means. You reverse it all. Thank you so much, sir. So if AC is the perpendicular bisector of BD and C is on AC, then CB is congruent to CD. Also, if AC is the perpendicular bisector of BD and A is on AC, then AB is congruent to AD. And now I'm going to blow you away, hopefully. Hopefully. If I tell you that AC is perpendicular bisector of BD, and I just put a random point here, F, guess what, guys? FD will be congruent to FB because it is a point on the perpendicular bisector. Powerful, powerful stuff here. Does this make sense, honestly? Yes, sir. Of F? Okay, think about it. AC is the perpendicular bisector, right? If a point, that means if any point on AC will now be equidistant to the endpoints of the segment that it is perpendicular bisector to. So let me erase it. Hold on. Okay, we know that AC is perpendicular bisector to BD, right? These are the endpoints of the segment that AC is a perpendicular bisector to, correct? So if I put a point F here, and it's on the perpendicular bisector, now FD will also be congruent to FB. And no, I'm not going to say it's like all radius are congruent. No, it's not. It's the converse of the equidistance theorem. It's completely different. Think about it like this, brother. AC is the perpendicular bisector of BD, correct? Right? A is a point on AC, correct? So isn't AB congruent to AD and CD congruent to CB? Okay. Well, isn't now F a point on the perpendicular bisector? So FB will also be congruent to FD. Let's do one more. No, you're welcome. Thank you for your honesty. Let's say I have here point E. Now that means that AD will be also congruent to AB. Any point on a perpendicular bisector will be equidistant to the endpoint of the segment that it is perpendicular bisector to. Thank you, my brother. God bless you. Yes, sir. Because of the base angle theorem, every single triangle that I put here would be isosceles. Yes. Okay, now, I know time is running out. So what I'm going to ask you for is a favor, okay? The bell's going to ring in about a minute and a half. I'm going to start my proofs. Go ahead. I know you need to go to class. I'm going to continue. I'm asking you like men to go home and watch these proofs because they're very important, okay? Don't make a lot of noise either when you're leaving because I'm going to be recording. And don't leave yet. I didn't say leave yet, please. I still got a minute. Give me my due respect. Okay, real quick. I have here given angle 1 is congruent to angle 2, which, of course, I did not label. So I guess pack up your stuff. I'll label them, and I will have the rest of this video up tonight. Thank you very much. Hope you learned a lot. Please watch the video. Oh, okay, sorry about that, guys. I forgot to label that angle 1, 2, 3, and 4. But now it is properly labeled. All right, let's check out this proof. I have that angle 1 is congruent to angle 2. Angle 3 is congruent to angle 4. And they want you to prove that line AE is a perpendicular bisector to BD. So, all right, let's get to it. Number 1, angle 1 is congruent to angle 2. That's given. Remember that we had an angle 1 here, 2, 3, and 4. So angle 1 is congruent to angle 2. Okay. I can easily now say that AB is congruent to AD because if the base angles are congruent, then the legs are congruent. Number 3. Angle 3 is congruent to angle 4. That is given. Okay? Now, BC is also congruent to CD because if the base angles are congruent, then the legs are congruent as well. Now look at what we have here, guys. AE is the perpendicular bisector of BD. AE is the perpendicular bisector now of BD. Now you may be saying to yourself, why? Well, think about it. Isn't point A on AC? Yes, it is. Isn't point C on AC? Yes, it is. Isn't AC equidistant to BD? And isn't point C also equidistant to BD? So if two points are equidistant to the endpoints of the same segment, then that segment is the perpendicular bisector of the second segment. So that is the equidistant theorem. Number 2, you're going to have to draw it all out here and actually put the given and the proof. They want you to prove that the line joining the vertex of an isosceles triangle to the midpoint of the base is perpendicular to the base. Well, as always, we're going to have to draw it out. So I'm going to draw out an isosceles triangle here, ABC, and I'm going to label AD as the line, okay, that is joining the vertex of the isosceles triangle to the midpoint of the base, okay? The given here. Well, the given here, D is the midpoint of BC for sure. And they also tell you that triangle ABC is isosceles. That's given. What do they want you to prove? They want you to prove in this case that AD is perpendicular to BC. So as always, went ahead and drew the figure here so we could mark our figure while proving. Number 1, triangle ABC is isosceles. That is given. Okay, since it is isosceles, AB is congruent to AC. That's definition of isosceles triangle. D is the midpoint of BC. That's given. Since D is the midpoint of BC, that means that BD is congruent to DC. Now, think about it, guys. Aren't both A and D equidistant to points C and B, which are the endpoints of segment BC? The answer is yes, they are. Okay? And sorry, BD is congruent to DC because definition of midpoint. So since both A and D are equidistant to the endpoints of segment BC, then for sure AD has to be perpendicular to BC. It's the equidistant theorem. In fact, not only is AD perpendicular to BC, but it's the perpendicular bisector of BC. So please focus on this because it's very, very important. Okay? Next and last, I have here that AB is congruent to AD. I have that BC is congruent to CD. I want to prove that BE is congruent to ED. Okay. Well, number 1, AB is congruent to AD. That is given. Number 2, BC is congruent to CD. That is given. Let's label. AB is congruent to AD. BC is congruent to CD. Number 3, AC has to be the perpendicular bisector of BD. Again, why? In this case, it's the converse of the equidistant theorem. Or actually, no, I believe it is just the equidistant theorem. Okay, because I have A is equidistant to both B and D. C is equidistant also to both B and D. So AC is the perpendicular bisector of BD. Why? Because just the equidistant theorem. I'm sorry, I messed up. Now, how do I prove that BE is congruent to ED? That is the converse of the equidistant theorem. Okay? Since BD is the segment that both A and C are equidistant to, that means that BE has to be congruent to ED. Why? Because E lies on AC. We already said that AC is the perpendicular bisector of BD. So if A is the perpendicular bisector on BD, any point on AC will also be equidistant to D and B. I suggest really taking your time with these proofs. Focus. Thank you for watching. God bless you. Hope you learned a lot and have a wonderful day. Thank you. Bye-bye.